Okay, so let me make it full screen. So today what we are going to see is we are going to see how to build an abstract interpreter for logic programs. So you can sort of think about this as just an interpreter for logic program. The keyword abstract is there for a particular reason. It might not be clear right now. Actually, it's mentioned here. So the idea is that we are abstract over the precise order in which we'll choose the rules and goals. Okay, so that's the reason why we are abstract in the interpreter. We will see how this actually is encoded. So the reason why you should focus on this lecture is that you will be implementing a concrete interpreter for logic programs, in particular Prolog, in your 7th assignment, the last assignment. So we will build this interpreter in Prolog, and what you will build is a Prolog interpreter that has all the bells and whistles, right? It will have some missing features like arithmetic, but it will have many of the useful features that you can start programming with the interpreter that you develop, right? So you're going to see the details of that in this lecture. So before we actually go on to look at the interpreter, we have to build up some basic functionality, which we will use later. Okay. So the first one is the substitution, right? So whenever we've been unifying terms in Prolog, we are implicitly doing substitution. Here we will formalize the notion of what substitution is, which will help you implement substitution according to the specification. Okay, so that's the idea. So a substitution is a finite pair of terms that is written this way, right? x1/t1, x2/t2 up to xn/tn, where each ti is a term. So it can be a compound term that is allowed by Prolog, and each xi is a variable. Okay, so what substitution is saying is that for the variable x1, go and substitute the term t1, and for variable x2, go and substitute the term t2, and so on. There are two well-formedness conditions for a substitution. So those conditions are the side conditions here, right? And the first condition simply says that xi not equal to ti. So what this says is you shouldn't have a substitution which just says go and replace the variable x with x, right? Even though this is idempotent, we are explicitly preventing that term from occurring in the substitution. And the second of these side conditions says that you shouldn't have two substitutions for the same variable. So this substitution shouldn't say for x go and substitute 0, and for x go and substitute 1. So this would be ill-formed, right? Which one should you substitute, 0 or 1? So this condition is preventing the same variable from occurring twice in the substitution, right? So these are sort of intuitive, just to prevent the substitutions from sort of being well-formed, right? And here is, and we write the empty substitution as epsilon, right? And here is an example of a substitution. Sigma here says that I'm going to describe a substitution, and it has three entries. First, it says go and substitute for x the term 1, 2, 3, the list 1, 2, 3. For y, substitute z. So substitutions can refer to other variables. That's totally fine. And for z, substitute the term f of a comma b, right? So this is a valid substitution. So here is a question, just to make sure we understand the ideas, right? Is this a valid substitution? Just consider the side conditions that I mentioned. Yes or no? No, right? Yeah, there are a few correct answers. So the substitution is invalid. The reason is that there are several reasons here. So the first thing is we shouldn't have a substitution of the same variable, right? We said these sort of substitutions shouldn't be allowed. So I have ZZ, so that should be prevented, right? and I have a variable a for which I have two substitutions, a a1, a2. So this is also not allowed. So the substitution, right? M/n is not valid. The left-hand side of the slash should be a variable. You can only substitute for a variable. You cannot substitute for any other term. So that's why this is invalid. But it's okay to have substitutions this way. This is completely okay. This term is okay. So what this says is wherever you find x, substitute y. Wherever you find y, substitute x, right? So the idea is that we are atomically going to apply all the substitutions. We are not going to apply one where we substitute all the x's to y and then apply substitutions y to x. So we'll take the term and then we'll say wherever you find x, substitute y. Wherever you find y, substitute x, right, on the original term. So this pair is totally fine, right? Okay, so that is substitutions. So we've defined what a substitution is. Next, we are going to define how to apply substitution to a term, right? What does it mean to apply substitution to a term? So firstly, we are going to see how to apply substitution to a variable. So we write application of the substitution sigma to a variable x as x sigma. So typically we write functions in the reverse order. This is just the syntax that is used by like logic programs, right? People who do logic programs prefer to write it in this syntax. So I'm being consistent with that. So the way to read this is we are applying the substitution sigma on this variable x. So what is the result of the substitution? If sigma has a term x/t, then the result of the substitution is t. For all other variables, right, x remains x. So for that particular entry, go and substitute it. For everything else, just leave it, right? And that's the meaning of applying a substitution to a variable. So we can extend this to apply substitution to arbitrary complex terms, right? So let sigma be a substitution. So here, right? And then E be a term or a formula. So we don't particularly care what that is. The application of the substitution to E, right, is obtained by simultaneously replacing all the occurrences of xi with ti, right? So you take all the occurrences of xi, replace that with ti on the original term, right? So what does this mean? Here is an example. So the substitution that I have is x1 to x, substitute with 1, 2, 3, y/z and z/fa comma b, and I have xyz, right? All you do is for x substitute 1, 2, 3, for y substitute z, and for z substitute a comma b. So this is how we apply a particular substitution to a term. So now, so because we've applied the substitution sigma to the term E, and we've got a new term, which happens to be a specialization of the original term E, right? So the term we will use is, we will call E sigma an instance of E. So E was more general, and we specialized it to E sigma, and we will call E sigma an instance of E. Okay, so that was applying substitutions to terms. If you sort of think about it, right? So substitutions are like functions, and in OCaml we've seen function composition. Take two functions and you can compose them together. So here what we are going to see is, we are going to see composition of two substitutions, right? We will go through what that means. So consider two substitutions, theta and sigma, right? And the composition of that substitution is written down as theta sigma. Intuitively, the meaning is that you will first apply the substitution theta, and then apply sigma substitution, right? So when I write the composition sigma theta, that gives, theta sigma, that gives me a new substitution, and the intuitive meaning is that you first apply the substitution theta, and then apply the substitution sigma, right? So you can define this as a substitution. So here is an example. So consider theta to be x/y and z/a, right? And sigma to be y/x and z/b. So what is the intuitive meaning? Wherever x is, you have replaced that with y, right? And wherever z is, you have replaced that with a. And on that term, right, you've replaced all the x's with y. So now you replace all the y's with x, right? And then replace all the z's with b. So if you sort of stare at it, right, if the original term that you apply the substitution, this composition of substitution theta sigma had an x, you replace x to y, and then you take the replaced y and replace that back to x, right? So you're going from x to y, then back to x. So as we saw earlier, we shouldn't have any substitutions x slash x. So essentially, we are not changing any of the x's that occur in the original term, right? So x slash y is gone, right? And we don't have x slash x, but we will retain y slash x, right? If the original term had a y, then this is not going to change that y. This initial substitution is not going to change the y, but the second substitution is going to change the y because I'm going to replace all the y's with x. So that is why y slash x occurs in the composition, right? And then look at what happens to z, right? So if the original term that you're substituting on had a z, all the z's have been replaced with a, right? And sigma says replace all the z's with b. But because we are applying z slash a first, all the z's have been replaced with a, right? There is no z's to replace here. So this is not necessary, right? And hence, we will only retain z slash a here, right? So that's the reason why the composition of these substitutions gave us y slash x, which is this one, and then just z slash b. We've thrown away, sorry, just z slash a. We've thrown away z slash b because there will be no z variable to replace in the composition. Okay, so this is just an example, right? So how do we formally define what should happen? So consider the substitution theta to be x1, s1, x2, s2, x3, s3 to xn, sn, and sigma to be y1, t1 to yn, tn. Let there be the two substitutions. I am defining composition theta sigma as this substitution here, right? What does it say? It says for all x1 to xn, just have those terms, but instead of substituting them with just s1, substitute them with the application of sigma on s1. So essentially what we're saying is because we will apply theta substitutions first you will replace x1 with s1, right? And if s1 happens to be a compound term which involves a variable, that is going to be influenced by whatever occurs in sigma, right? So that is why we are saying take this s1, apply sigma on it. So that will be the final substitution, right? And then all of the y1, t1 remains the same up to y1, yn, tn, except that you have to take care of two conditions, precisely the conditions that we took care of here, right? So if you simply applied this formula right here, what will happen? So we have x, y, where we substitute y with x here. So we will end up with x slash x for the substitution here. And of course, well-formless condition on substitution tells us that x slash x should not be present. So, so we have this first side condition which says that remove all xi slash si sigma for which xi is the same variable as si sigma. So if you end up with x slash x, don't include it, is what we are saying, right? You have to go through all of this x1 to xn. If you ever happen to have x1, x1, x2, x2, or xn, xn, remove that. That's the first one. And the second one handles the case that has to do with the fact that z slash b is not present in the final one. Why does that happen? Because these two substitutions happen to be on the same variable. Since this substitution happens first, this is no longer necessary, right? This is not going to be there. It's not going to be useful. So that is what we write down here. So we remove all those substitutions yi comma ti, where yi is the same as some xj, right? So we remove z comma b from the final one because there happened to be a z comma a in the first substitution, right? So if you apply this algorithm, right, whatever is written down here, you will go from this example to what we have here. So that is composition of two substitutions. Um, so we are slowly building up to an interpreter, right? Substitution is the key aspect of this. We will see. We'll slowly build it up. But any questions on this so far? So this is just a matter of just following the rules, right? And the rules are, I mean, they have some corner cases, but otherwise there is nothing surprising here. Okay, so let me continue further. So, so we have some nice properties for substitutions that we've defined so far. So let theta, sigma, and gamma be substitutions, epsilon be an empty substitution, and let E be the term or a formula, right? Then substituting in E, the composition of the substitutions theta, sigma is the same as first applying the substitution theta on E and then applying sigma on E, right? So this equality holds. And the substitution is associative, right? So I am applying substitutions first theta, then sigma, then gamma. Actually, the way to read this is I'm first applying the composition theta sigma and then applying gamma. This is the same as applying theta followed by the composition of sigma gamma, right? This equality also holds. If you have an empty substitution, then this one goes through. So that is totally fine. So if you take an empty substitution and apply the substitution theta on it, it is the same as applying an empty substitution, composing theta with an empty substitution, which is the same as theta. And finally, if you take some substitution theta, right, and you apply theta and you compose theta with itself, then it is only equivalent to theta if and only if the domain and the range of theta don't intersect, right? This is the domain and this is the range, right? They don't intersect. If they do intersect, then you will have an effect applying theta twice, right? For example, consider theta to be x slash y, y slash x, right? Then theta theta is essentially going to do first replace all x's with y, y with x, and then going to put it back, right? It replaces all y with x and x with y. So in essence, theta theta is the empty substitution, which is not the same as theta. The issue here is the domain and the range intersect, right? But if the domain and the range do not intersect, if it's an empty set, then it will be the case that theta theta will be equal to theta. You can work it out, right? So here is an example, but this holds in general. So these are some nice properties that we have for substitutions. In general, composition of substitution is not commutative, right? So associative property holds, right? The composition of substitutions is associative, but it's not commutative. For example, consider the composition here, right? So for any x, replace with fy, and then replace the y with a. So this will be equivalent to the substitution where x is replaced with fa, because we replace y with a, and then replace any y with a, right? This is not the same as the substitutions composed in the other order, right? Other way, other direction. So if you have first apply ya, then apply x slash fy, then we will be left with the composition of this is going to be replace all y with a, right, and replace all x with f of y. So these two terms, this term and this term, are not the same, right? So composition of substitution is not commutative. Okay, so we've seen a lot about substitutions. Now we are going to think about unifiers, right? Unifiers are the mechanism by which we are going to perform unification, which lies at the heart of how Prolog does computation, right? So what is a unifier? Let S and T be two terms, right? These are two compound terms. These can be any term, right? S and T be two terms. Let sigma be some substitution, right? We call the substitution a unifier for S and T if sigma applied to S and sigma applied to T are syntactically equal, right? So given two terms, you have a substitution, and we call the substitution a unifier if you can apply the substitution to both of these terms and get the same term, syntactically same term, right? So here is an example. So let the term S be f of x comma y, where x and y are variables, and t, the term t be f of g of z comma z, right? And you can have a unifier for this one. First, let's consider the unifier sigma, right? So if you replace x with gc, so this x gets replaced with gc and this y with z, right? Which will be the same as this term here now, right? Here we have no substitution for the variable z. So applying sigma on t will give you the same term, but applying sigma on s will give you term t, right? So sigma is said to be the unifier for these terms. So unifier is how we compute what are the substitutions that are necessary for unifying two terms, right? And it is not the case that there is only one unifier for a pair of terms if there exists a unifier, right? So theta is also a unifier. Theta says that for x, replace that with GA, right? X gets replaced with GA, Y gets replaced with A, and Z gets replaced with A, right? So both of these terms end up being f of G of A, comma A, right? So theta is also a unifier for the terms S and T. So both sigma and theta are unifiers for the S and T. But there is something about sigma that is more preferable, right? Um, and that is formalized by this property called more general, right? The substitution sigma here is said to be more general than the substitution theta if there exists a substitution omega such that you can obtain theta, the more specialized one, by composing sigma with omega, right? What does that mean? So the more general substitution is actually specifying less about the variables, right? And the less general one, theta, here, for example, if you see in this substitution sigma, we leave the z as z, right? This variable z remains z, right? But here we are saying the variable z is replaced with a, and we also have this particular substitution where we replace z with a. So we sort of prefer the sigma more than theta, right? So we call sigma more general than theta. And in particular, what is this omega for these two terms? The omega for these two terms is going to be z slash a. What does that mean? If you take z slash a, right, and compose that with sigma, right, you will end up with theta. So how does this work? So wherever you find z, replace that with a. So this becomes x slash g of a, which is this one, y slash a, right, which is this one, and then you also include z slash a here. So hence we call sigma to be more general than theta. Okay, so we have this, we are building this property of more general one. So given two terms, right, you can have multiple substitutions, and one is more preferable than the other, right? So the natural question is, if there are multiple substitutions and we can compare them, right? one where one is better than the other one, is there one that is the best among these substitutions, right? What is the unifier that is the most general for two terms? So given two terms, they might not unify, right? But if they do unify, there must be the unifier which is the most general. So how do we define this most general unifier? A unifier is said to be the most general unifier. So we write MGU because we'll keep using this idea over and over again. So the most general unifier of two terms is by definition, right? It is more general than any other unifier of the terms. So if the two terms unify and you have an MGU, then by definition it must be the case that it is more general than any other unifier, right? So it turns out that a pair of terms may have more than one most general unifier, right? So this term most is sort of not, I mean, it's superlative, but there can be equivalent ones there. So this is surprising. Let's look at an example. Example is quite easy actually. So consider the terms f of x comma x and f of y comma z, right? Uh, and for these two terms, do these terms unify? Yes, they do. So if they do unify, what is the most general unifier? You can think of at least two terms here, right? The first one is going to say, the first one is theta, which says replace x with y. So x with y. So this term becomes f of y, and z with y. So this term also becomes f of y, right? And we can have another MGU, sigma, which says replace x with z. So this term becomes f of zz, and y with z. So this term becomes f of zz, right? And both of these terms are most general unifier because they are just replacing things with variables, right? Um, and yeah, in particular, you can take theta, right? You can get theta by taking sigma and replacing the z's with composing that with z slash y, right? So if you compose that with z slash y, you get x slash y. So you get y here. We drop it, and you get z slash y, which is theta, right? X slash y, z slash y is theta. And similarly, you can get sigma from theta by composing that with y slash z, right? So if you replace y with z here, you get xz, right? And this y replaces to z, but we get zz, we drop it, and we include yz. So you get sigma. So theta and sigma are both MGUs, right? How do you define equivalent MGUs? If we have two MGUs, theta and sigma, then there exists a substitution, right? Which is gamma, which only renames variables. So this is a substitution, but it only replaces variables with variables, other variables, where x1, y1 to xn, yn are just variables. So if you do that, if you are able to do that, then we call theta and sigma to be both MGUs. Sir, so Raghu has a question. Will MGUs always exist? If two terms unify, MGUs will always exist. So because by definition, right, two terms unify, then there must be a unifier, right? And it could be a unique unifier or multiple unifiers. And what we've seen is, given two unifiers, you can order them, right? By finding a substitution such that one can be composed to get the other one. So you keep doing this until you are left with equivalent ones, which are all from which can be obtained by just replacing the variables this way. Oops, yeah, this way. So if two terms can be unified, then there does exist at least one most general unifier, right? And you can have multiple most general unifiers. And we will see an algorithm for computing most general unifier. But it might be the case that the two terms might not unify, right? That's a separate question. Yeah, and the intuitive meaning here is if you have multiple MGUs, then one can be obtained from the other by just renaming variables. Okay, so here's a question. We've seen a bunch of ideas, right? So Raghu has a follow-up question. Given any two unifiers, is one of them always more general than the other? Need not be, right? So here we have two terms. We have theta and sigma. Because we have this substitution zy, right? Sigma is more general than theta, but we also have a substitution yz where we get sigma from theta. So neither sigma nor theta is more general than the other one. So they are both equivalent, but they are both the most general unifiers here. Does that answer your question, Raghu? The other case when neither exists. Oh, I see. Okay, so you have two unifiers, but they are not comparable. Okay. Um, you can have two unifiers. I'll have to think about it. I don't know the answer offhand, but you can always compute MGUs. Good question. I don't have an answer to your question right away, and I don't want to say something that I don't know anything about. I'll come back to your question. Okay, good. So, so here's the question, right? What is the most general unifier of these two terms? 1, 2, 3, 4. Which one? Yeah. So Harini has the right answer. 1 is the answer, right? 3 is not the answer because if you do 3, yeah, Raghu I think has got it. So if you do just 3, this A will not be replaced. So 1 is the answer. So you replace X with A, Y with A, and Z with A. I think this particular example is quite nice. If you understand how to get the most general unifier for this one, I think most cases are covered. Almost all of the cases are covered. So let's go through this, right? First, we can rule out 4 because if you just don't do the substitution, they are not syntactically the same. We can rule out 3 because if you just replace X with Y, Z with Y, we have an A here. This Y remains here. They are not syntactically equal. If you if you do this substitution, where you replace the variables with B, this atom A, right, remains here, and this will be B. They are not the same, and hence the MGU has to be this. So you replace X with A, Y with A, and Z with A. Everything will be F of A. Okay, so that's the MGU. So I can't show this nicely in this one, but I can do this. So here is the algorithm, a nice algorithm for computing the most general unifier. Is this readable? Can you read this? Is the font size too small? Okay. So if this is readable, okay, that's good. So I have given you properties about most general unifier, right? What we will do in Prolog, right? Whenever we unify two terms, we are trying to find the most general unifier so that we can perform the substitutions, right? So what you need is an algorithm for computing the most general unifier. So there is a question. So there's a question by Naman. Are terms A and B in the syntactically equal? No, they are not, right? So, oops. So A is an atom, B is an atom. They are not syntactically equal. So by syntactically equal, I just mean string equality, right? If you compare them using string equality, then they have to be the same term. Does that answer your question? If they are variable, they have to be the same variable. If they are an atom, they have to be the same atom. If they are function symbols, then you recursively do the same. They have to have the same top function symbol. They have to have the same arity, and then recursively they have to be the same. Right. So that is what I mean by syntactically being equal. So A and B are not the same atom. Okay. So here is can epsilon ever be the most general unifier? Yeah. So if you get the same term, right? If I have f of x, or just AA, right? Atom AA, then the unifier is epsilon, and that is the MGU. Actually, yeah. So yeah, that's an example. Anyway, so let me carry on. These are very good questions. I encourage you to think about it, but I think I'll start with this algorithm just so that I can make enough progress. Yeah, but if we have variables, then we can find a more general unifier. Um, yeah, I think the unifiers really make sense when you have variables, right? If you don't have variables, you either have fully ground, you only have fully ground terms. When you have fully ground terms, the only way they unify is they are syntactically equal, right? By definition, there are no variables. So unification becomes like trivial, right? They are either the same string or not. Uh, does that give you an intuition, Sarthak? Okay. Uh, so here is an algorithm for computing the MGU. What you will do in the 7th assignment is essentially encode this algorithm. It's a really simple algorithm. It actually works out quite nicely, right? So the input for this algorithm is the two terms for which you're going to find the MGU, right? Um, and to be unified on the MGU, I think this is. I think I should fix this. Two terms to be unified. Oops. So the input for this algorithm is the two terms T1 and T2 that to be unified. The output is going to be theta. Theta is the most general unifier. If T1 T2 unifies, it might be the case that T1 T2 does not unify, in which case we just raise fail exception. Right? This is pseudocode. This is not OCaml code, but you'll get the idea, right? So the algorithm goes like this. So so it takes the two terms x and y, right, and the current most general unifier, right? So we'll see how we plug this in initially. What you do first is you first apply theta to x and theta to y and get x and y again. So first you apply them to the terms x and y. So you get x. I use the term x and y again, and there are 4 rules, right? So the rules are, if x is a variable, right, and that does not occur in y. So this is the occurs check that we are doing, right? So if x is a variable, y may be anything else. If it does not occur in y, then all we do is we say take the thing that you've been passed, the MGU that you've been passed, and compose that with x/y. Essentially, go ahead and perform this substitution in that, compose that with this theta, right? Bear with me, this might not make sense right now. We will go through an example, it will make sense. So the next case is the opposite one, right? Where y is a variable, x happens to be some compound term, and if x does not, y does not occur in x, y is a variable, y does not occur in x, then you do the flip, the opposite way, right? So you take theta and then compose that with y/x, right? If x and y are identical constants or variables, you just return theta. So there is no new information that is produced. So you just return theta. If x is a compound term, fx1 to xn, y is a compound term, y1 to yn. If these two x's are different, yeah. So the question you're asking is whether if x and y are two different variables, right? X and y could be. So then the first rule will apply. So no. Can you clarify, Naman?
Sir, like above the rules that you have written x equal to x theta, and in the rules x is a variable. These x's are different, right? Or is it the same x?
I'm just using the same variable name. So x is a term, right? All I'm saying is apply theta on this term, and you're going to get a result. So this is x, and I'm sort of following OCaml syntax here. So that x is now shadowed. All you have is the same, this x in the SQL. Does it make sense? Yes, no?
Like, so this x that you have defined, so this x is this is the x that you are using in the rules, right? We are checking if that x
Yeah,
is
yeah. So x is, so this x is sort of a meta variable, right? So this is not a variable in Prolog sense. This is some x in the language. X could be x. X is just a term, right? I think I should have used T1 T2 here. If I just use T1 T2, right? This is just a some term. And the term could itself be a variable or an atom or a compound term. Does that make sense? Or if you have, or we can try again.
Where you are using terms and where you are using variables.
So okay. So this, whenever I write x and y here, right? These are just terms, right? And so what I'm checking here is x is a variable, right? I am explicitly checking whether the term happens to be a variable here, right? And I'm checking whether y is a variable. I'm explicitly checking whether the term is a variable. See, I think imagine x to be t1 and y to be t2, right? That's what I'm expecting here. I just happen to use x and y because I didn't want to use subscript everywhere. But anyway, so let's go through this, right? So if x and y terms are identical constants or variables, then there is no influence on theta, so we just return theta as it is. But these x and y terms could be compound terms, right? So I am actually pattern matching here. So I am saying if x is f and x1 to xn, y is also f y1 to yn. So what I'm checking is x and y are two terms which have the same function symbol, top function symbol f, right? And the same arity, then do something. Otherwise, return fail, right? If x happens to be a term which is foo of 1, and y happens to be a term which is bar of x, bar of z or something, then this pattern will not match. You have to raise fail because these two terms do not unify. Implicitly, what I'm writing down here is by using the same variable name here, I'm sort of saying these two top function symbols should be the same. And by using the same number of arguments here, I'm also saying that the arity is the same, right? That is the implicit assumption here. So if x and y happen to be two compound terms with the same top function symbol and the same arity, then what you do is you fold over a list of pairs of x and yn, right? So bear with me, just look at it. We'll go through an example to make this clear. The idea is that you take x1, y1, x2, y2, x3, y3. You put that in, right? x1, y1, x2, y2, x3, y3 up to x and yn. and then you fold over it. You're going to basically write a for loop over it. You initially start with the for loop is going to return some MGU. You start with the MGU that was passed in, right? And at each step, what you're going to do is take the MGU, the current accumulator MGU, take the pair of terms that you're trying to unify, compute the MGU of that, right? That is going to return some MGU, and this is going to be fed to the next iteration, right? You are essentially applying this MGU for each of these pairs of terms. And finally, what's going to come out is an MGU, or it can raise an exception if it calls fail, because this is a recursive call. If it comes out, it is going to come out with an MGU, which is the most general unifier for these two compound terms, right? So this is written in very much a functional fashion. So that's the algorithm. I haven't told you how it actually works. I've only told you what it is, right? So the initial call to this algorithm, since it takes a theta, you initialize that with this empty substitution first. Okay, so that's the algorithm. Let's actually work through an example that makes everything much simpler, right? So this is the quiz that I asked, right? This question that I asked. Let's see how this algorithm works for this particular example. So the two terms are f of, let me move it here, f of x, xy, f of y, za, right? So I'm going to call MGU on these two terms. So I'm going to call this, which is going to call MGU of the two term epsilon, right? MGU of these two terms epsilon. So the first thing that is going to happen is we are going to apply epsilon. So if you go through here, right, x is going to be this term, this y is going to be this term. Again, I'm sort of mixing up the variable here with the meta variables here, but I think it will be clear. So we are applying the substitution. So what I'm doing here is x theta, right? And what it is here is applying epsilon on this term first, and applying epsilon on the second term. Of course, epsilon is an empty substitution, right? So it's not going to have any influence. And you have four cases, right? None of these three cases apply, right? Because these two cases apply only when one of the terms is a variable. Both the terms are compound terms, right? Yeah, and this is checking for either they are a variable or a constant. They are not variable or a constant. So we are going to come to the fourth case. What is the fourth case? Fourth case says that these two terms should have the same top function symbol. They have the same top function symbol f, right? They have to have the same arity. They do have the same arity, right? And it's going to do this fold. This fold is going to be done, right? I'm writing down the fold explicitly here. So it's a fold, fun theta, x comma y. I'm just using x comma y here. MGU of xy theta, MGU of xy theta, right? The initial theta that we get passed here is an epsilon. So that becomes epsilon here. And this is constructed by zipping together these arguments, right? x1, y1, x2, y2, x3, y3, up to x and yn. Here we have x comma y, x comma z, and y comma a. We have y comma a, right? And how does so we are going to evaluate this fold, right? How does the fold work? You can think of this as fold L, right? I'm just writing fold. It doesn't matter which direction it goes. Let's go from left to right. So the first, in the first iteration of the fold, right? This x is going to be x, y is going to be y, right? And this theta is going to be epsilon. And you're going to call MGU of xy epsilon, right? So this is the recursive call. It goes here, right? And the first thing you're going to do is x equals x theta and y equals y theta, which is equal to why have I written this way? So x equals x epsilon, so that becomes x. Y equals y epsilon, that becomes y. It just does not change, right? And then you come in, you go to the cases, right? The first case says that if x is a variable that does not occur in y, x is in fact a variable, right? X is a variable, and that does not occur in y. Y is also a variable; it does not occur there. In which case, all you do is you take this theta and then compose it with x slash y. You take this epsilon and compose that with. Actually, this is not necessary. Um, Let me remove this, then continue. So you take this epsilon and then compose that with x slash y, right? Because epsilon is an empty substitution. If you compose, you get the substitution, same substitution again, right? You get x slash y out. So all you're saying is, in order to unify x and y, right, you replace x with y, and you get the same term, and that's the most general unifier. So that is the result of one recursive call that comes out of this fold, right? And you call fold again, right? Fold continues for the next iteration, which is what I've written out explicitly here. So that theta that comes out, I've written it here as x comma y. And then we have completed the iteration for the first of the element, right? And we have two more left. We have two more left. And we do the fold again, right? What does fold do? Fold goes ahead and matches with these and calls MGO again. So now MGO is called on x, z, and x slash y. And that is the result of the first recursive call, right? That came out. So x slash y. So the first thing you do now is apply this substitution on the two terms. If you apply x slash y on x, right, you get y, right? You get y here. Maybe I can make it a little bit bigger. Yeah, okay. You get y here, right? And then if you apply x slash y on z, you get z out, right? That does not change because we are not replacing z here. Now the question is, we go through these cases, right? And we hit the first case again. If the first term is a variable and does not occur in y, the first term is a variable, right? Y is a variable that does not occur in z. Then the result is take the current theta and then compose it with x slash y. Take the current theta, which is x slash z here, and compose that with y slash z. So what happens here? Apply the rules for the composition. So this becomes x slash z and y slash z, and that is the MGU now, right? That comes out again because we are in this fold call now, right? That comes out again, and you have one more iteration of fold left. So the thing that you have is this term that has come out. You have one more term, which is y slash a, which is the y slash a here, right? And do one more iteration of the fold. So what happens here is the terms that you have is y and a, and the theta that you have is this term here. First, you apply this substitution on the two input terms. So if you apply this substitution on y, we have a substitution which says y should be z. So this term becomes z. And if you apply substitution to an atom, nothing changes, right? A remains a, right? So you have z and a. And again, the first rule will apply, right? If x is a variable that does not occur in y, z is a variable that does not occur in the term a, right? Atom is a term which does not certainly have z. So what you do, you take the current theta and then compose it with x slash y. You take the current theta, which is this term, and apply z slash a on it. So what do? You replace the z's with a, and then you also add z comma a here, right? So this becomes xa, ya, za, xa, ya, za, and you're done with the fold, right? When you're done with the fold, you just return that. You just return that result out as a result of the initial call, and what you get out is x slash a, y slash a, z slash a, which is x slash a, y slash a, z slash a, which is the result of which is the most general unifier for these two terms. So that's how this algorithm works. I've taken a lot more time than I should. Quickly, any questions on this? Just work through this example by hand, and you'll see that it just works out. I haven't given you the proof of correctness or anything, why this should produce the most general unifier. But anyway, so any questions? No questions? Okay, in that case, I'll stop here. I think we can finish this in the next class. Thank you.